Our final talk before our break at 3 is Frank McCormick. He's the program manager of the Air, Water, and Aquatic Environments program in the Rocky Mountain Research Station of the Forest Service. He has 17 years of experience managing natural resource programs as an ecologist and program manager with the EPA and Forest Service. He holds a doctorate in zoology from the University of Oklahoma and has research interests in fish and aquatic ecology.
I'd like to thank the organizers for inviting me, though I will confess that when Darren first contacted me and extended the invitation, my first reaction was, what were they thinking? For after all, I have never done research in the Great Basin, have no real connection to it in terms of folks in my program, other than a few who have done a little bit of work there. Don't really know enough about it to be conversant with it, other than at one point when I was with the Washington office in the Forest Service, I wrote a talk for the Associate Deputy Chief for Research to go and give at a Great Basin conference. So if that's the link, I offer you my sincere apologies and hope that when I'm done that you don't find yourselves thinking, what were the organizers thinking? I should apologize to Olivia Salmon for what must have appeared to her as stony silence on my part when she asked me, as a follow-up to a question that Brett Roper had asked me, what I was thinking about talking about, because to be quite candid, I'd really given it no clear thought. But this struck me as being an opportunity for some discussion and for some thought. I have managed to root out a little bit of data from various components of both my past and from our program, and so hope that it'll paint the picture that I was after. This is lifted almost directly from the Rocky Mountain Station's strategic framework, a document that sort of outlines what our general research perspective is, and it very well fits the work that's done in the Air, Water, and Aquatic program. And so I'm reasonably comfortable with the fact that we operate as a group in sort of that interface among terrestrial and aquatic ecosystems and in an environment heavily influenced by fire. It's also a useful point of discussion because it emphasizes the importance of interdisciplinary work that I think is embodied by the folks who are in the room, and helps us consider the context in which our environments in the Rocky Mountain region are operating, both in the terms of the pressures of increasing human demands as the U.S. population shifts more to the west and places greater demands on those resources, both for recreation and for public consumption, but also in the context of probably the most urgent and emerging issue that confronts us, and that is the changing climate in the West, and the pressures that will also place on these important resources. This is a map of the Hayman Fire in Colorado. It's relevant because it's representative of one of the more severe wildfires in recent history. It delivers, to this day, a tremendous amount of sediment, despite remediation efforts, into a municipal water supply, and at the same time shows significant input from a variety of nutrients from the surrounding soils through the groundwater and through surface water runoff into the municipal water supply, which affects water quality, and people don't like it when their water quality is affected, especially when you're metropolitan Denver. As an example of human demands, these represent the points of diversion on the Salmon River, which, if you're familiar at all with the Idaho batholith and central Idaho, that's the Frank Church River of No Return wilderness area, and despite that, there's a fair amount of diversion for public water use or for agricultural water use from the wilderness area. And in terms of just an overall terrestrial effect, probably nothing is more charismatic for the Rocky Mountain region than the mountain pine beetle infestation. Not obviously something that's of great concern to folks in the Great Basin, but certainly something that is indicative of the interaction of climate change with our ecosystems, and so for the long term with ramifications for the Great Basin, especially if, as some of the climate models have predicted, ultimately the southern Idaho Snake River Plain and northern Nevada will more resemble the Sonoran and Chihuahuan deserts. So where do we begin with restoration? This is mostly to plant a seed for a little bit later. This is the Climax mine, for those of you who don't know it. One of my first field trips as a government employee was to the hard rock mining region of central Colorado, and you cannot work for the Environmental Protection Agency for very long without developing a morbid appreciation for disturbance. But in the general context, restoration, at least as far as I thought about it for the talk, had largely been focused on improving structure and moving from some sort of degraded condition, such as you might have seen in the Climax mine, to some more idealized, desired condition. We've started, I think, more recently to think of this as much in terms of process as in terms of species structure or community composition. And I would argue that relatively few restoration efforts now consider moving from a degraded condition to some sort of semblance of the historic structure without consideration of the restoration of the ecological processes that were common or that we think may have been typical of the more desired conditions. The idealized situation would be that we move from degraded condition up to this idealized desired condition with a sort of conterminous or concomitant increase in structure and improvement in process. But the reality is that we move through a variety of scenarios, often improving processes such as the restoration of fire in order to move to a combination of restored function and restored structure. Though, as you start talking about fire and fire-prone systems, the public reasonably asks a lot of questions such as, well, how much fire and how much fire is appropriate? In fact, that was the question that was asked by one of the forest rangers, forest supervisors, at a recent conference where we were having a discussion about wilderness areas and the appropriate use of fire. Typically, when we think of disturbances in a general context, the tendency had been to think of them as a disturbance event with consequent longer-term restoration to some sort of stabilized system. But in the context of most of the systems that we're dealing with, especially now, we're dealing with multiple and cumulative disturbances across an aquatic system. And so these are, if you think of them as sort of a pulse disturbance and a response, or some sort of disturbance and response, now you almost want to think of it in the context of cracking the whip with when you were in a playground and kids were using a jump rope, where they're flipping it multiple times and you're sending a series of or cumulative set of disturbances through a system, and the system responds over much longer periods of time. So if we think about restoration now in the context of, did I skip one? In the context of climate change, we have some sort of disturbance, stress, and response, trying to move your restoration endpoint towards some targeted desired condition where you're dealing with that very simplified, very stylized pulse disturbance move to a restoration endpoint. It's relatively straightforward, and from a management perspective, it's probably a lot easier to move to that desired or to get closer to your targeted endpoint. But in the context of climate change, we've introduced a moving target. And so now the probability or the likelihood that we will actually come fairly close to our targets is reduced because we're in an ever-changing milieu where the climate, the drying, the changes in precipitation, the changes in temperature are moving the environment that we're trying to hit farther and farther away from us as an endpoint for restoration. And so just as likely an outcome would be that we would miss it entirely because it has moved completely away from where we think we want it to be or where we were concentrating our efforts at the time. This might appear familiar to some economists. This is an adaptation of what's known as Medowar's curve, where you have risk and benefit on the two curves, and it's an investment concept where you try and maximize the return on your investment by assuming a certain amount of risk. This was all obviously prior to September of 2008. But anyway, the idea being that somewhere with some intensity of treatment, you reap some benefits of that treatment, and the idea would be to push your restoration effort up to the top of that curve. Jack had a curve very similar to that. This is the one that he called the difficult management decisions, where your intensity of treatment would have to go on for a very long time before you begin to reap any benefits. This is actually in the wrong place. It probably is better placed down there. But often what we'll find is that you'll invest in some sort of treatments, and then at some point, even though you would continue to apply, and I think Jack talked about this a little bit, even though you would continue to apply a fair amount of effort and a fair amount of resources to a restoration effort, the immediate benefits drop off fairly quickly, and you can plot a variety of scenarios under that. The one that the management side would really prefer is one that's very predictable. The one that's missing here is Jack's low-hanging fruit, which was the easy choice one. But what would actually be is probably the most desired scenario is where we can say, with a predicted amount of investment and a predicted approach for restoration treatments, we get a predicted level of benefit. The difficulty there is there's not enough data and not enough money for us to be able to develop that sort of scenario in a reliable frame. There are some exceptions, and this is more of a plea for data, and I think one of the speakers this morning said that we don't need to continue to monitor, and I'm not sure I would agree with that. One of the reasons I say that is because the availability of long-term data have allowed us to do a number of things. This is a map showing the distribution of sites where air temperature have been recorded for a period of time, and where bull trout, a native species that's dependent on a very narrow regime of temperatures in streams, both for persistence and for spawning purposes, where it's distributed and where temperature data from those streams have been collected. When you look at what the predicted or what the thermally stable temperatures for the bull trout populations in the Boise River Basin were in 1993, and contrast that with the current distribution, or the distribution in 2000 as of 2006. This is a publication by one of the scientists in our program. You look at the distribution or the changes, and there are between 8 and 16% per decade loss in suitable stream habitat for these fish, and air temperature and summer stream flow account for a fairly high level of the ability to predict those losses in habitat. What that's allowed us to do is draw an overall scenario of future climates. This is also something that they're working on for the cutthroat trout that Brett was talking about earlier. Could be done for just about any species. The one area I'd like you to remember is that one right there. That's the garbage drainage in northern Nevada that was of considerable interest to the Senate Majority Leader in a conversation with our station director, who was asked directly, "What are you doing for bull trout conservation in northern Nevada?" And perhaps the question should be, what should we be doing for bull trout conservation in northern Nevada? Because under a variety of climate scenarios, there's really nothing we can do to ensure its persistence. So never underestimate the power of data. The combination of having some riverine temperatures, stream temperatures, flow data, red counts allow us to make certain predictions about the likely persistence of species, and thus allow us to make some prioritized decisions about where our restoration efforts might be most effective. just a warmer climate or stream temperatures, but it's also drier. This is a recent paper by one of the scientists in the program who looked at, and again, the value of historic data, from a nearly 50-year record of stream gauges and precipitation, was able to show that the dry years over that 50-year period were actually getting drier. The trend was that streams were drying more than they had been at the beginning of that period. This has ramifications for the points of diversion that I showed you on any one of the systems in the West, where as habitat for fish becomes increasingly under pressure by increasing demands for water withdrawals, how do you make those decisions in the scenario where there's a shifting, there's a trend in the resource that's clearly declining? Among the things that this has important considerations for are the endangered species. This is the publication from the American Fisheries Society of, I think, last year, looking at the native fishes of North America and Mexico and identifying the sources or the causes as much as possible for their decline in their threatened or in their endangered status. And if you look, the two primary causes were habitat loss, associated then with stream drying, and very narrow ranges. That's not grazing. I'm not going to implicate grazing as a source of decline of native fishes. I would never do that in a public forum. But those two things, the very narrow distribution of species, particularly in the West, and as Brett mentioned, particularly in the Great Basin, where in many cases they're restricted to very narrow ranges, as you change the hydrologic regime and change the temperature regimes in which they are expected to persist, those reductions will place even greater pressures on those fishes, and there will be resulting conflict between human use and the needs for native resources. Mining is a fairly significant legacy for the Forest Service and the Bureau of Land Management. This is just the northern end of the Great Basin, showing all of the abandoned mine lands. These are not active mine lands, these are abandoned mine lands, either for coal and natural gas, shales, you name it, but particularly hard rock mining. And the hatched areas in blue are impaired waterways associated with those old mine legacy projects in various places. The resources necessary to complete a restoration of abandoned mine lands exceed all of the possible estimates that the federal budget could possibly provide us. There are thousands of them in the West. There are somewhere between 50 and 70,000 in the Great Basin. And so an almost insurmountable task, but relevant to the population centers because these have significant negative impacts on water quality. Heavy metals are often a byproduct of hard rock mining. They leach into stream systems where communities in the West draw their water from surface waters, and those surface waters are contaminated by everything from zinc to cadmium to chromium. Poses a serious health risk to the population. So it's not something that we can just ignore. The relevance to this, having the data to make these decisions is really the point here. Being able to characterize the biological condition, looking at its status, knowing the importance, and that's the importance to land managers and the importance in the performance of the ecosystem. The biological conditions that are associated with the fragmentation or habitat losses for these species give us some idea of what the value is, and allow us to place some sort of value on that resource. By combining that with some measure of the risk to that resource, we can then come up with some recommendations for management practices. Again, the power of data. Rocky Mountain Station has 18 experimental forests and ranges that range from just up near the Canadian border to just down near the Mexican border. So they span the range of both desert to montane ecosystems, extremes of precipitation and temperature, and gradients from east to west, north to south that represent a very good long-term data record for both hydrology and vegetation. One of the purposes here is to urge people to delve into this with colleagues in the Forest Service, because it's a tremendous resource. We should be thinking, though, not just in terms of what the legacy data, what the last, in some cases, 100 years worth of data can tell us, but what the next 30 years of data can tell us if we come up with a coherent approach and make some decisions about the kinds of data that we want to collect for these things to answer questions that might come up 30 years from now. This could just as easily be PIBO, but since I worked for the EMAP program, this is another one. There was an entire issue of the Journal of the North American Benthological Society that came out last year inviting people to get into these data. This is the National Wadable Streams Assessment from the Environmental Protection Agency. They collected a fairly large number of sites, I think nearly 1,400 sites in 2003. They just completed their second 5-year cycle. These data are publicly available, and scientists were invited in the JNABS publication to participate in an analysis of these data. One of the things that's possible with this is to look at the relative extent. Since it's a probability-based survey, you can actually get an estimated extent of the resource. You can calculate based on the extent of the disturbance from things like nitrogen or in-stream fish habitat. You can get estimates of the relative risk and calculate the attributable risk, which would allow us in the long run to make decisions about not just the risk, but make prioritization decisions about restoration. And I think that's my last slide. Thank you.
Time for several questions.
Yes. Well, one of the short. I'm sorry, I'll repeat the question. The question was, if you look at the wadable streams assessment and overlay that with a distribution of stream gauges and precipitation gauges, there's a bit of a disconnect, and how would we make those two things? The answer is not an easy one. If you're not familiar with the way that those data were, or the sites were selected, they're based on a probability framework where the river reach is laid out and then a point is randomly selected. So much like the National Atmospheric Deposition Program, you'd have to do some sort of kriging exercise in order to get some sort of map that showed more of the climatological influence. The data for the wadable streams assessment is very site-specific. It has both water quality and physical habitat data associated with it, and a fair amount of, I think it's macroinvertebrate and algal data, but not resident fish. The solution, of course, is always more money, but there are some limits. And that's the point about the power of networks, is figuring out where the best placement and how to prioritize the placement of the kinds of measurements that we would put in the environment.